A galaxy sits in space, glowing with the light of hundreds of millions of stars. Nothing unusual, except for one detail. The light reaching our telescopes left that galaxy 13.5 billion years ago, when the universe itself was barely 300 million years old. At that point in cosmic history, galaxies like this one should not exist. Yet there it is, and it is not alone. We have found hundreds more, each one shattering what we thought we knew about how the universe began. If you find this intriguing, consider subscribing to see where this mystery leads. Brace yourselves. We begin. Deep in the constellation Fornax, a telescope captured something that should not exist. The James Webb Space Telescope pointed its mirror at a tiny patch of sky, no bigger than a grain of sand held at arm's length. In that darkness, among thousands of distant galaxies, one object glowed with a peculiar red hue. Scientists labeled it Jadus, a name that would soon become infamous. The initial measurements seemed wrong. Impossible, even. The team ran the numbers again. Same result. This galaxy existed just 290 million years after the Big Bang. To understand why this matters, picture the universe as a human lifetime of 80 years. At that scale, this galaxy appeared when the cosmos was barely 6 months old. Galaxies are not supposed to form that quickly. They need time to gather gas, condense matter, ignite stars. The universe at 300 million years old was still cooling from its violent birth. The first atoms had only recently formed. Darkness still dominated most of space. Yet here sat this object, blazing with starlight across 13.5 billion years of space. The discovery happened in January of 2024, but the detection itself occurred months earlier. The JADES team, short for James Webb Advanced Deep Extragalactic Survey, was hunting for early galaxies. They expected to find small, faint objects, baby galaxies taking their first breaths. Instead, they found a giant. The galaxy measured over 1,600 light-years across. For comparison, that distance would take our fastest spacecraft over 28 million years to cross. Scientists needed to confirm the finding. One fuzzy image could be a mistake, a trick of the light, an artifact in the data. They turned the telescope back toward that same spot. They used different instruments, different filters, different wavelengths of light. Every test confirmed the same shocking conclusion. The confirmation came through spectroscopy, a technique that breaks light into its component wavelengths, like a prism splitting white light into a rainbow. This revealed the galaxy's redshift, a measurement of how much the universe's expansion had stretched its light. The number came back as 14.32. No galaxy had ever been found with a higher redshift. No object had been confirmed at such an extreme distance. The previous record holder sat at redshift 13.2, existing 400 million years after the Big Bang. JADES pushed that boundary back by over 100 million years. This was not just another distant galaxy. It was not even the most distant by a small margin. It represented a leap into territory that cosmologists believed would remain hidden for years, maybe decades. The team published their findings with cautious language, but the implications rang clear. If galaxies this developed existed that early, then our timeline of cosmic evolution had major gaps, big gaps, the kind that forced scientists to reconsider fundamental assumptions. But the distance alone did not trouble astronomers the most. What really kept them awake at night was what came next. Light moves fast, but space is vast beyond comprehension. When you look at a star, you see it as it was years ago. The light you perceive left that star's surface before it began its journey across the void. Our closest stellar neighbor, Proxima Centauri, appears as it was 4 years in the past. Light from the Andromeda Galaxy shows us that galaxy as it existed 2.5 million years ago. We peer into history every time we gaze upward. This is not theory. This is confirmed fact. proven through countless measurements and observations. Now imagine pushing that concept to its extreme limit. The light from Jades has been traveling for 13.5 billion years. When that light began its journey, Earth did not exist. Our solar system had not formed. The Milky Way was barely recognizable. The universe itself was a fraction of its current age. That photon of light has crossed incomprehensible distances, racing through expanding space at 186,000 miles per second, never stopping, never slowing, for longer than complex life has existed anywhere in the known cosmos. Think of it this way. If you could somehow send a message to that galaxy today, traveling at the speed of light, it would arrive 13.5 billion years from now. By then, our star will have died. Earth will be gone. The universe will be vastly different, if it still exists at all. This creates a strange paradox. We see the galaxy as it was in the ancient past, but we exist in its distant future. The galaxy we observe might not even be there anymore. It could have merged with others, been torn apart by cosmic forces, or evolved into something unrecognizable. We will never know its current state. The universe's expansion ensures that we can only ever see its infant form, frozen in time by the speed of light. But there is something even stranger at work here. As space itself expands, it stretches the light traveling through it. A photon that left Jades as ultraviolet radiation arrives at our telescopes as deep infrared light. The wavelength has been pulled longer, stretched by the cumulative expansion of billions of years. This stretching, called redshift, happens to all light from distant objects. The farther away the source, the more severe the redshift. At a redshift of 14.32, the light from this galaxy has been stretched by a factor of over 15. Every wavelength we detect has been pulled to more than 15 times its original length. This means that the galaxy's actual appearance would be completely different if we could somehow see it up close. The colors would be shifted. The brightness would be intensified. The whole galaxy would look alien compared to its redshifted image. Scientists use this redshift as a cosmic ruler. By measuring how much the light has stretched, they can calculate how far away an object sits and how long ago the light was emitted. The math is complex but reliable. It rests on well-tested physics. When astronomers say Jades existed 290 million years after the Big Bang, they are not guessing. They are reading the universe's own signature embedded in the light. Yet even with this confirmation, questions lingered. How did anything manage to form that early? The answer grows more disturbing with each detail. 300 million years sounds like a long time, but in cosmic terms, it is barely an instant. The Big Bang did not immediately create galaxies. For the first 380,000 years, the universe was too hot for atoms to form. Matter existed as a dense plasma, opaque to light. Photons could not travel freely. Everything was fog. Then, as the universe cooled, electrons combined with protons to form the first hydrogen atoms. Light suddenly had room to move. Astronomers call this moment recombination, and it marks the point when the universe became transparent. But even after recombination, the cosmos remained dark. No stars had formed yet. No galaxies glowed. The universe entered what scientists call the Dark Ages, a period when only neutral hydrogen filled space. This hydrogen collected into vast clouds, drawn together by gravity and dark matter. These clouds slowly collapsed, growing denser and hotter until pressure and temperature reached critical points. Then, nuclear fusion ignited. The first stars were born. These early stars were nothing like the ones we see today. They were massive, perhaps hundreds of times heavier than our closest stellar neighbor. They burned incredibly hot and bright but died quickly, exploding as supernovae within a few million years. Their deaths scattered the first heavy elements into space: carbon, oxygen, nitrogen, iron, the building blocks of planets and life. This process takes time, lots of time. For a galaxy like Jada's to exist at 300 million years after the Big Bang, everything in this chain of events had to happen faster than models predict. The dark matter halos had to form, the gas had to collapse, stars had to ignite, live, and die. Then, somehow, those stars and gas had to organize into a coherent galaxy structure over 1600 light-years across. Current simulations suggest this process should take at least 500 million years, possibly longer, yet here sits evidence that it happened in 300 million or less. That leaves only two options. Either the simulations are wrong, or something about the early universe worked differently than we thought. Some researchers proposed that the first stars formed earlier than previously believed, perhaps within 50 million years of the Big Bang. If true, that gives more time for galaxies to develop. But even this acceleration barely solves the problem. Building a galaxy requires more than just stars. It requires those stars to gather into a stable structure, bound by gravity, rotating as a collective unit. Random stars scattered through space do not make a galaxy. They need organization. That organization takes time. Others suggested that star formation in the early universe was far more efficient. Maybe nearly all the available gas converted into stars, rather than the typical 20% or less we observe in later galaxies. This would allow galaxies to grow massive quickly, but this creates its own problems. Where did all that gas come from? How did it collapse so fast? Why don't we see this efficiency in younger galaxies? Every explanation requires stretching our understanding of physics or revising established theories. And Jada's was just the beginning. Astronomers found others, dozens of them, all sitting in the same impossible timeline, all defying predictions. The crisis was not one galaxy, it was a pattern. The size of these galaxies made everything worse. Galaxies grow slowly, or so we thought. Imagine trying to build a city in 6 months. Not a small town, but a sprawling metropolis with millions of inhabitants, complex infrastructure, and organized districts. You would need materials, labor, planning, and time to coordinate everything. Now imagine doing this while the ground beneath you is still forming. That is essentially what Jada has accomplished on a cosmic scale. The galaxy stretches over 1600 light-years from edge to edge. To put that in perspective, if you could travel at the speed of light, crossing this galaxy would take 16 centuries. That is longer than recorded human history. And this entire structure assembled itself in less time than it takes some stars to complete their life cycle. The trouble is not just the raw size, it is how that size came to be. Galaxies form through the gradual accumulation of matter. Dark matter creates gravitational wells that pull in hydrogen and helium gas. This gas compresses, heats up, and forms stars. Those stars cluster together, attracted by each other's gravity. Over millions of years, these clusters merge and grow. The process is slow, methodical, and predictable. Or it should be. Jades had no time for slow growth. At 290 million years after the Big Bang, the universe barely had enough time for the first stars to form, let alone die and contribute heavy elements to later generations. Yet this galaxy managed to pull together enough matter to create a stable structure spanning 1600 light-years. The speed of assembly defies conventional models. Scientists estimate the galaxy contains several 100 million times the mass of our nearest star. That is a conservative guess based on the light output. The actual mass could be higher. All of that matter had to come from somewhere. It had to travel across space, fall into a dark matter halo, compress into stars, and organize into a rotating galactic disk. The timeline simply does not allow for it under normal circumstances. Some researchers pointed to the possibility of primordial density fluctuations. These are tiny variations in the distribution of matter right after the Big Bang. In regions where matter was slightly denser, gravity pulled in more material, creating the seeds of future galaxies. If Jades formed in a particularly dense region, it might have had access to more raw material than typical early galaxies. But even this explanation has limits. Density fluctuations can only do so much. They might give a galaxy a head start, but they cannot account for the sheer size and organization observed in this object. The galaxy is not just large, it is coherent. It has structure. That structure implies multiple generations of star formation, feedback processes, and gravitational settling, all of which take time. The size also affects how we interpret the galaxy's light. Larger galaxies can host more stars, which means more light output. But if the galaxy is truly this large, then the brightness we observe becomes even harder to explain. The stars would need to be incredibly luminous, burning through their fuel at rates that seem unsustainable. We will get to that problem soon. For now, consider this. Jades represents just one example. Astronomers found others nearly as large, all clustered in the same early epoch. If one massive galaxy existing that early is a puzzle, finding dozens suggests something fundamental about our cosmic timeline is off. The mass calculations only deepen the mystery. Hundreds of millions of stellar masses do not appear from nothing. Mass is the most fundamental property of a galaxy. It determines how strongly the galaxy pulls on surrounding matter, how fast its stars orbit, and how it interacts with neighboring structures. Measuring the mass of a distant galaxy is not straightforward, but astronomers have methods. They analyze the galaxy's light, estimate the number of stars, and calculate total mass based on known stellar populations. When scientists ran these calculations for Jades, the numbers came back absurd. The galaxy appeared to contain several 100 million times the mass of our closest star, possibly more. To build that much mass, you need an enormous amount of raw material and enough time to gather it all together. 300 million years after the Big Bang, the universe barely had either. Consider the available matter. After the Big Bang, the universe consisted mostly of hydrogen and helium. These elements made up over 99% of all ordinary matter. Everything else, the carbon, oxygen, and heavier elements, came later through stellar processes. The total amount of matter in any given region of space was fixed by the initial conditions of the universe. You could not create more matter. You could only gather what already existed. For Jades to reach its observed mass, it needed to collect gas from a huge volume of space. That gas had to fall into the galaxy's dark matter halo, compress, and form stars. But gravity works at a finite speed. Matter can only fall inward so fast. Even under ideal conditions, there are physical limits to how quickly a galaxy can accumulate mass. Those limits make the existence of this galaxy problematic. Astronomers compare the galaxy's mass to predictions from computer simulations. These simulations model the early universe using the best available physics. They account for dark matter, gas dynamics, star formation, and gravitational interactions. When run forward in time, they show how the first galaxies should form. According to these models, galaxies at redshift 14 should be small. They should contain maybe a few tens of millions of stellar masses at most, not hundreds of millions. Jades exceeds those predictions by nearly tenfold. That discrepancy cannot be explained by small errors or uncertainties in the models. It represents a fundamental mismatch between theory and observation. Either the models are missing key physics, or the measurements are somehow off. Extensive follow-up observations confirmed the measurements. That leaves the models. One possibility involves the efficiency of star formation. In modern galaxies, only about 20% of available gas converts into stars. The rest is blown away by stellar winds, supernova explosions, and radiation pressure. But what if early galaxies were different? What if they converted 50, 60, or even 80% of their gas into stars? That would allow galaxies to reach higher masses much faster. However, this explanation requires understanding why early galaxies would behave so differently. What mechanisms would prevent gas from being expelled? Why would star formation be more efficient then compared to now? The physics governing star formation should not change drastically based on cosmic age. Gravity, pressure, and nuclear fusion operate the same way regardless of when they occur. Another idea focuses on the initial conditions. Perhaps certain regions of the early universe had more matter than others, creating dense pockets where galaxies could form rapidly. These overdense regions would act as cosmic assembly lines, churning out massive galaxies far earlier than expected. But finding dozens of such regions, all producing massive galaxies, suggests this was not rare. It suggests the early universe was fundamentally different than our models assume. The mass problem connects directly to another puzzle. Where did all that light come from? Light reveals what matter alone cannot hide. When the James Webb Space Telescope captured JADES, the galaxy stood out immediately. Not because of its size or distance, but because of how bright it appeared. In astronomical terms, brightness is quantified as magnitude. Lower numbers mean brighter objects. JADES registered at an ultraviolet magnitude of -20.81. For a galaxy that far away, existing that early, this brightness is staggering. Brightness tells us how much light a galaxy emits. More light usually means more stars, since stars are the primary light sources in galaxies. But there is a limit to how many stars a galaxy can pack into a given volume. There is also a limit to how bright individual stars can be. Massive stars burn brighter, but they also die faster. Finding a galaxy this luminous that early challenges both limits. Let me put the brightness in perspective. Imagine you light a candle in a completely dark room. Now imagine placing that candle 10 miles away and trying to see it clearly. That gives you a sense of how faint distant galaxies appear. The fact that we can detect JADES at all means it is pumping out an incredible amount of light, not just for its distance, but for its age. The galaxy emits light across multiple wavelengths. Astronomers detected it in near-infrared, mid-infrared, and even caught hints in other bands. This broad spectrum indicates active star formation. Young, hot stars radiate most of their energy in ultraviolet light, which gets redshifted into the infrared by the time it reaches us. The strength of this emission suggests the galaxy is forming stars at a prodigious rate, possibly hundreds of stellar masses per year. That rate seems impossible for the available gas supply. If the galaxy formed stars that quickly for very long, it would exhaust its fuel within a few tens of millions of years. Yet it appears to be going strong at 290 million years after the Big Bang. Either it had access to a vast reservoir of gas, or something else is boosting its luminosity. Some scientists suspected the brightness might come from a supermassive black hole at the galaxy's center. These black holes, often millions or billions of times heavier than individual stars, can outshine entire galaxies when they actively feed on surrounding material. The infalling matter heats up to extreme temperatures and radiates enormous amounts of energy before crossing the event horizon. This process creates what astronomers call an active galactic nucleus, or quasar. If JADES hosted such a black hole, it could explain the excessive brightness without requiring unrealistic numbers of stars. But there is a problem with this idea. The galaxy is too large and too extended for its light to come mainly from a central point source. Observations show the light distributed across the galaxy's 1600 light-year span. A quasar would appear as a bright spot at the center. This looks different. Additionally, forming a supermassive black hole that early introduces its own set of problems. Black holes grow by accreting matter or merging with other black holes. Building a black hole massive enough to power a bright quasar in less than 300 million years requires rapid growth rates that push theoretical limits. We will explore this dilemma in detail later, but for now, the important point is that the quasar explanation does not quite fit the observations. That leaves stars as the primary light source, and if stars are producing this much light, the galaxy must be forming them at rates that seem incompatible with our understanding of early cosmic conditions. The brightness mystery is not solved. It is just beginning to reveal deeper complications. What came next challenged expectations even further. Elements heavier than helium do not exist in the primordial universe. When the Big Bang occurred, it produced hydrogen, helium, and trace amounts of lithium. That was it. No carbon, no oxygen, no iron. These elements, which we take for granted, had to be forged later inside stars. Stars are cosmic factories, converting lighter elements into heavier ones through nuclear fusion. When massive stars die in supernova explosions, they scatter these newly created elements into space. Over time, this enriches the surrounding gas with metals, as astronomers call anything heavier than hydrogen and helium. This process requires multiple generations of stars. The first stars form from pure hydrogen and helium. They live, die, and pollute their environment with heavier elements. The next generation of stars incorporates these metals, creating even more complex chemistry. Eventually, after several cycles, the gas becomes rich enough in heavy elements to form planets, asteroids, and potentially life. That is the standard story. It takes time, lots of time, at least several 100 million years of stellar evolution. So when astronomers detected oxygen in Jades, they knew something was wrong. Not just traces of oxygen, but significant amounts, enough to show up clearly in the galaxy's spectrum. Oxygen requires multiple generations of massive stars to produce in observable quantities. Those stars must form, burn through their fuel, and explode. Their debris must mix with the surrounding gas. Their new stars must form from that enriched material. All of this needs to happen before the galaxy reaches 290 million years of age. The timeline does not fit. The first stars probably took at least 50 million years to form after the Big Bang. That leaves roughly 240 million years for everything else. In that span, you need the first generation of stars to complete their lifetimes, which for the most massive ones takes about 3 to 5 million years. Then you need the second generation to form, which takes another few million years. If you are very generous with the timelines and assume everything happened at maximum speed, you might squeeze in 3 or 4 generations of stars. Maybe. But the amount of oxygen detected suggests more than just a few cycles. It suggests the galaxy was chemically mature, with stellar populations that had been enriching the gas for a substantial period. One research team estimated the galaxy had about 10 times more heavy elements than expected for its age. That is not a small discrepancy. That is a fundamental breakdown in our timeline of chemical enrichment. The oxygen detection came from a different telescope, the Atacama Large Millimeter Array in Chile. This instrument observes light at millimeter and sub-millimeter wavelengths, which are sensitive to emission from oxygen ions in distant galaxies. When ALMA pointed at Jades, it picked up a clear signal. The presence of oxygen was confirmed. No room for doubt. This created a new problem. If galaxies could achieve chemical maturity that quickly, what does that say about the pace of cosmic evolution? Were stars forming faster than we thought? Were they dying more quickly? Or did the first generation of stars produce far more heavy elements per supernova than modern stars do? Each possibility requires rethinking established stellar physics. Some scientists proposed that the first stars were extremely massive, perhaps 200 or 300 times heavier than our nearest stellar neighbor. Stars that massive would burn incredibly hot and bright, living only 1 million years or so before exploding. They would also produce copious amounts of heavy elements in their cores. If the early universe preferentially formed such monsters, it might explain the rapid chemical enrichment. But why would the early universe favor extremely massive stars? Current star formation theory suggests that stars form across a range of masses, from tiny dwarfs to massive giants. The distribution should be similar regardless of cosmic age. Changing that distribution requires altering the fundamental conditions under which stars form. Perhaps the lack of heavy elements in the primordial gas affected how clouds collapsed. Without metals to cool the gas efficiently, maybe only very large clouds could collapse, leading to very massive stars. This remains speculative. What is certain is that the oxygen detection in Jades indicates a level of stellar activity and chemical evolution that should not be possible in such a young universe. And as more observations came in, the problem only grew worse. The galaxy was not alone. Hundreds of them appeared where only a few should exist. When the James Webb Space Telescope began surveying deep space, astronomers expected to find early galaxies. They expected small, faint objects scattered sparsely across the cosmic landscape. What they found instead was a population explosion. Everywhere they looked in the distant universe, bright red galaxies stared back, so many that researchers struggled to explain their abundance. These galaxies earned a nickname, Little Red Dots. The name comes from their appearance in JWST images. They show up as small, reddish points of light, their starlight heavily redshifted by cosmic expansion. Each one represents a galaxy seen as it existed in the first billion years after the Big Bang. The color indicates distance. The farther away, the redder the light. By late 2024, astronomers had catalogued over 300 of these little red dots at extreme redshifts. Some sat at redshift 9, others at 10, 12, or even higher. Each one pushed the boundaries of what early galaxy surveys predicted. According to pre-JWST models, finding even a few dozen galaxies at these distances should have been difficult. Finding hundreds suggested the models badly underestimated the abundance of early galaxies. The problem extends beyond sheer numbers. Many of these galaxies appear surprisingly massive and bright. They rival or exceed the mass of the Milky Way, despite existing when the universe was only a few % of its current age. Building that much structure that quickly requires extremely efficient star formation and matter accumulation, processes that should not be possible under standard cosmology. Several explanations emerged to account for the little red dots. One idea suggested that many of them host actively feeding supermassive black holes. The black holes generate intense radiation that makes the galaxies appear brighter than they would from starlight alone. This additional light could trick mass estimates, making the galaxies seem more massive than they truly are. When astronomers account for black hole contribution and subtract it from the total luminosity, the galaxies shrink to more reasonable sizes. This explanation works for some cases. Follow-up spectroscopy of specific little red dots revealed signatures of black hole activity. Broad emission lines, high ionization states, and rapid variability all pointed to central engines feeding on gas. But not all little red dots show these features. Many appear to be genuinely dominated by starlight. Their spectra match what you would expect from massive stellar populations, not from quasar-like activity. Another hypothesis focused on dust. Dust absorbs blue and ultraviolet light while allowing red and infrared light to pass through. Dusty galaxies appear redder than they actually are. If the little red dots contain significant amounts of dust, their colors might be misleading. This could affect distance estimates derived from color alone. A closer, dustier galaxy might masquerade as a more distant one. However, spectroscopic follow-up on many little red dots confirmed their extreme distances. The redshifts measured from spectral lines matched the photometric estimates. These galaxies were genuinely far away, not nearby imposters hidden behind dust. The dust explanation failed to account for the majority of objects. That left a third possibility. The little red dots are exactly what they appear to be: massive, star-forming galaxies that assembled rapidly in the early universe. This interpretation challenges our understanding of galaxy formation timelines but fits the observations most consistently. It also implies that the early universe was a far more active and dynamic place than previously believed. The abundance of these galaxies raised another question: where did they all come from? Forming one massive galaxy ahead of schedule is unusual. Forming hundreds suggests something systematic about the early universe that our models do not capture. Either the initial conditions after the Big Bang were different than assumed, or the processes governing star and galaxy formation operated under different rules. Researchers scrambled to update their simulations. They tweaked parameters, adjusted star formation efficiencies, and explored different cosmological scenarios. Some models managed to produce more early galaxies by assuming very efficient star formation or by modifying the properties of dark matter halos, but none could fully reproduce the observed abundance and masses without breaking other established constraints. The little red dot phenomenon was not isolated, it was systemic, and it pointed to deeper issues with our cosmic timeline. Those issues became clearer when scientists examined the dark matter halos. You cannot see dark matter, but its absence would be catastrophic. Dark matter makes up about 85% of all matter in the universe. It does not emit, absorb, or reflect light, making it invisible to telescopes. We infer its presence through gravitational effects. Galaxies rotate too fast to be held together by visible matter alone. Clusters of galaxies bend light from background objects more than their observable mass should allow. These phenomena point to vast amounts of unseen matter permeating space. In the early universe, dark matter played a crucial role in galaxy formation. After the Big Bang, tiny fluctuations in density created regions where dark matter began to clump together. These clumps grew through gravitational attraction, forming structures called dark matter halos. Ordinary matter, the hydrogen and helium gas, fell into these halos, attracted by their gravity. Once concentrated, the gas could cool and form stars. Without dark matter halos to act as gravitational scaffolding, galaxies would not exist. The number and mass of dark matter halos at any given time depend on the universe's age and the properties of dark matter itself. Cosmologists can predict how many halos of a certain mass should exist at different epochs using simulations based on the lambda CDM model. This model incorporates dark matter, dark energy, and ordinary matter, and it has successfully explained numerous observations of the universe's structure. According to lambda CDM, the early universe should have relatively few massive dark matter halos. Small halos form first, then merge over time to create larger ones. At 300 million years after the Big Bang, most halos would be small, capable of hosting only modest galaxies. Halos massive enough to support galaxies like Jada's should be exceedingly rare, maybe a handful in the entire observable volume surveyed by JWST. Yet, JWST found hundreds of massive galaxies at that epoch. Each one requires a massive dark matter halo to provide the gravitational well needed to gather and retain gas. The sheer number of these galaxies implies far more massive halos than predictions allow. Either the predictions are wrong, or something else is happening. One possibility involves the nature of dark matter itself. Lambda CDM assumes dark matter is cold, meaning it moves slowly and clumps efficiently. But what if dark matter is slightly warm, moving faster and smoothing out small-scale structures? Or what if dark matter interacts with itself in ways we do not understand, altering how halos form and merge? Changing the properties of dark matter would change the halo mass function, potentially creating more massive halos earlier. However, any modification to dark matter properties must not conflict with other observations. Dark matter's behavior affects galaxy rotation curves, the cosmic microwave background, and large-scale structure formation. Tweaking dark matter to fix the early galaxy problem might break something else. Researchers explored these possibilities carefully, and most concluded that dark matter modifications alone could not solve the halo abundance issue without creating new conflicts. Another approach questioned the efficiency of galaxy formation within halos. Perhaps early halos were exceptionally good at converting their gas into stars. If every halo, regardless of size, formed galaxies much more efficiently than modern ones, then fewer massive halos would be needed to explain the observed galaxy abundance. Smaller halos could host surprisingly massive galaxies. This idea shifts the problem from dark matter to baryonic physics, the processes governing ordinary matter. But it introduces the same question we have encountered repeatedly. Why would early galaxies behave so differently from later ones? What physical mechanism would cause such high efficiency in the early universe, but not now? Feedback from supernovae and stellar winds should work the same way across cosmic time. The fundamental physics does not change. Some researchers propose that the little red dots are not all galaxies. Maybe some are primordial black holes, massive objects formed directly from density fluctuations in the early universe rather than from collapsing stars. If true, these black holes could shine brightly by accreting gas, mimicking the appearance of galaxies without requiring the same halo structures. But spectroscopic observations largely ruled this out for the majority of objects. Their light signatures match stellar populations, not accreting black holes. The dark matter paradox remains unresolved. We need more massive halos than theory predicts to explain the abundance of early massive galaxies. No simple adjustment to lambda CDM seems to fix the discrepancy without causing problems elsewhere. This forced scientists to consider more radical possibilities. What if the problem was not with dark matter, but with how stars formed? Stars do not usually form efficiently from available gas. In modern galaxies, star formation is a wasteful process. Only about 10 to 20% of a galaxy's gas gets converted into stars. The rest is expelled by powerful stellar winds, radiation pressure from young stars, and supernova explosions. This feedback prevents galaxies from turning all their fuel into stars, regulating their growth and maintaining a balance between gas accretion and star formation. This inefficiency is well documented. Observations of nearby galaxies show large reservoirs of unconverted gas. Theoretical models explain why feedback mechanisms eject gas before it can form stars. The physics makes sense. Young, massive stars produce intense ultraviolet radiation that heats surrounding gas, increasing its pressure and causing it to expand outward. Supernovae inject energy into the interstellar medium, blowing gas away from star-forming regions. These processes limit how efficiently galaxies can form stars. But jades and the other little red dots seem to violate this rule. Analysis of their stellar masses and light output suggests they converted a much higher fraction of their gas into stars. Estimates range from 50 to 80% efficiency, far above what modern galaxies achieve. If accurate, this means early galaxies were extraordinarily good at making stars. Why would early galaxies be more efficient? One hypothesis centers on the lack of heavy elements. In modern galaxies, metals in the gas help cool it by radiating energy away. Cooler gas collapses more easily, but it also allows feedback mechanisms to be more effective. Without metals, the primordial gas in early galaxies cooled differently, perhaps settling into denser configurations that resisted disruption by feedback. This could allow more gas to reach the densities required for star formation. Another idea focuses on the strength of feedback itself. Early stars were likely more massive on average than modern stars, due to the lack of metals affecting how gas clouds fragmented. Massive stars produce powerful winds and end in energetic supernovae, but they also have shorter lifetimes. If these stars burned through their fuel and died before their feedback could expel significant amounts of gas, the galaxy might retain more fuel for subsequent star formation. This scenario requires precise timing and conditions, but is not impossible. Researchers also considered the role of dark matter halos. Early halos might have been denser and more compact than their modern counterparts. A denser halo exerts stronger gravity, making it harder for feedback to eject gas. The gas remains trapped, forced to form stars, even in the face of energetic stellar winds. This would increase star formation efficiency without requiring changes to the stars themselves. Each explanation has merit, but none fully accounts for the observations. The efficiency required to explain jades is extreme. It pushes the boundaries of what seems physically plausible, and the fact that so many early galaxies show similar characteristics suggests this was not a fluke. It was the norm. This revelation has profound implications. If early galaxies formed stars far more efficiently than later ones, it means the history of star formation in the universe does not follow a smooth, predictable curve. There was a period, early on, when galaxies behaved fundamentally differently. They grew faster, converted gas more completely, and assembled massive structures in record time. Then, at some point, this behavior changed. Galaxies became less efficient, more regulated, more like what we see today. What caused this transition? Why did star formation efficiency decrease over cosmic time? These questions have no clear answers yet. Some researchers speculate that the increasing abundance of heavy elements changed the thermodynamics of gas, making feedback more effective. Others suggest that the structure of dark matter halos evolved, becoming less able to retain gas against feedback forces. Both ideas remain speculative. The star formation efficiency shock is one piece of a larger puzzle. It connects to the mass problem, the brightness mystery, and the timeline crisis. Together, these issues paint a picture of an early universe that was far more active and dynamic than our models anticipated. But there was another layer to the mystery, one that involved black holes. At the heart of most large galaxies sits a supermassive black hole. These objects contain millions or billions of times the mass of a typical star, compressed into a region smaller than our solar system. They exert immense gravitational pull, warping space-time around them and dominating the dynamics of their host galaxies. We have observed supermassive black holes in galaxies across the universe, from nearby neighbors to distant quasars, billions of light years away. The presence of supermassive black holes in the early universe raises immediate questions. How did they form? How did they grow so large, so quickly? Black holes can only grow by accreting matter or merging with other black holes. Both processes take time. An individual stellar mass black hole, formed from a dying star, might weigh 10 to 50 times the mass of that star. Growing that to 1,000,000 or billion times requires consuming vast amounts of gas or countless mergers. Astronomers calculate that even under ideal conditions, with continuous accretion at maximum rates, a stellar mass black hole needs at least hundreds of millions of years to reach supermassive status. This timeline works fine for black holes in older galaxies, but finding supermassive black holes in galaxies less than 500 million years after the Big Bang presents a problem. There simply has not been enough time, yet observations confirm their existence. Some of the little red dots show spectroscopic signatures consistent with actively feeding black holes. Broad emission lines, high energy radiation, and variability patterns match what we see in quasars. These galaxies host black holes actively accreting gas, shining brightly as material spirals inward and heats to millions of degrees before crossing the event horizon. One proposed solution involves primordial black holes. Instead of forming from dying stars, these black holes would have formed directly from density fluctuations in the early universe, mere moments after the Big Bang. If conditions were right, regions of slightly higher density could collapse directly into black holes without going through the stellar phase. These primordial black holes could be much more massive from the start, giving them a head start on growth. The idea is tantalizing but controversial. Primordial black holes have never been directly observed. We have no confirmed evidence they exist. Theoretical models allow for their formation, but the conditions required are very specific. The density fluctuations must be large enough to overcome pressure, but not so large that they disrupt the overall smoothness of the universe. Finding the right balance is tricky. Even if primordial black holes exist, growing them to the observed masses in early galaxies still requires rapid accretion. Black holes have a theoretical limit to how fast they can consume matter, called the Eddington limit. Above this rate, the radiation pressure from infalling material becomes so intense that it pushes away additional gas, choking off further accretion. To exceed the Eddington limit, special conditions are needed, such as super-dense gas clouds, that funnel matter directly into the black hole without triggering runaway radiation pressure. Observations of some early galaxies suggest their black holes might be accreting above the Eddington limit, a phenomenon known as super-Eddington accretion. If true, this could explain how they grew so massive so quickly, but super-Eddington accretion is difficult to sustain for long periods. The intense radiation generates strong outflows that eventually shut down the accretion process. Balancing rapid growth with these self-limiting mechanisms is challenging. Another complication arises from the relationship between black holes and their host galaxies. In the modern universe, the mass of a galaxy's central black hole correlates tightly with the mass of its bulge, the central concentration of stars. This suggests a co-evolution, where the black hole and galaxy grow together, influencing each other through feedback processes. But in the early universe, this relationship appears disrupted. Some galaxies host black holes that are disproportionately massive compared to their stellar mass. The black holes grew faster than their host galaxies, violating the established correlation. This mismatch hints at different formation pathways or evolutionary tracks in the early universe. Perhaps black holes formed first, then attracted gas that later formed stars. Or maybe the feedback mechanisms that regulate black hole and galaxy growth were weaker or absent early on. Either scenario requires rethinking how supermassive black holes and their host galaxies develop. The black hole confusion adds yet another layer of complexity. Solving it requires understanding not just how black holes form and grow, but how they interact with their environments under the extreme conditions of the early universe. The answer might lie in how we measure distance itself. The universe is expanding, and that expansion leaves a signature. When light travels through expanding space, its wavelength stretches. This stretching is called redshift because visible light shifts toward the red end of the spectrum. Infrared light shifts even further, into wavelengths our eyes cannot see. The amount of redshift depends on how much space has expanded during the light's journey. Distant objects, whose light has traveled longer, show greater redshift than nearby ones. Redshift provides astronomers with a cosmic clock. By measuring how much a galaxy's light has redshifted, they can determine how far away it is and how long ago the light was emitted. The relationship between redshift and distance is not linear due to the universe's changing expansion rate, but it is well understood. Observations of the cosmic microwave background, distant supernovae, and galaxy surveys all calibrate this relationship with high precision. For jades, the measured redshift of 14.32 translates to a look-back time of about 13.5 billion years. The galaxy existed when the universe was roughly 290 million years old, just 2% of its current age. This conversion from redshift to time relies on our understanding of cosmology, specifically the lambda CDM model. If that model is correct, the timeline is correct. But if the model has flaws, the timeline could be off. Some researchers questioned whether the lambda CDM model accurately describes the early universe. The model assumes certain properties for dark matter, dark energy, and ordinary matter. It predicts how fast the universe should have been expanding at different epochs. But what if those assumptions are wrong? What if the expansion rate in the early universe was different than currently believed? If the universe expanded faster than lambda CDM predicts, then high redshift galaxies would be younger than we think. A redshift of 14 might correspond to 500 million years after the Big Bang instead of 300 million. This extra time could ease the tension between observations and theory. Galaxies would have more time to form stars, accumulate mass, and develop chemical complexity. However, changing the expansion rate is not trivial. It requires modifying fundamental parameters in the cosmological model. These parameters are tightly constrained by multiple independent observations, including the cosmic microwave background, the distribution of galaxies, and the abundance of light elements formed in the Big Bang. Adjusting one parameter to fix the early galaxy problem might throw off these other observations, creating new conflicts. Another consideration involves the accuracy of redshift measurements themselves. Redshift can be measured in two ways. photometrically and spectroscopically. Photometric redshift uses the color of a galaxy, comparing its brightness in different filters to estimate how much its light has been redshifted. This method is fast, but less precise. Spectroscopic redshift analyzes the galaxy's spectrum, identifying specific emission or absorption lines and measuring their shift directly. This method is slower but far more accurate. Many of the little red dots were initially identified using photometric redshifts. Critics worried that some might be closer than claimed, their colors distorted by dust or unusual stellar populations. If even a fraction of the high redshift galaxies were actually lower redshift imposters, it would reduce the severity of the early galaxy problem. But follow-up spectroscopy confirmed the distances for many objects, including JADES. The redshifts are real. The galaxies are genuinely that distant and that early. The redshift revelation is that the universe's expansion provides an independent, reliable way to measure cosmic time. Barring dramatic revisions to cosmology, the timelines derived from redshift measurements are trustworthy. JADES-GSZ140 really did exist, less than 300 million years after the Big Bang. The little red dots really do populate the early universe in surprising numbers. The observations are not flukes or errors. They are reality, and they demand explanation. This brings us back to the telescope that made these discoveries possible. Infrared vision changes everything. The Hubble Space Telescope revolutionized astronomy during its 3 decades of operation. It captured stunning images of distant galaxies, nebulae, and star clusters, expanding our understanding of the universe's scale and structure. But Hubble had limitations. It observed primarily in visible and near ultraviolet light. For the most distant galaxies, whose light has been redshifted into the infrared, Hubble could not see them. They remained hidden, invisible to its cameras. The James Webb Space Telescope was designed to overcome this limitation. Its instruments operate in the infrared, specifically the near and mid-infrared ranges. This allows it to detect light from the most distant galaxies, whose visible and ultraviolet emissions have been stretched into infrared wavelengths by cosmic expansion. JWST does not just see farther than Hubble. It sees different kinds of objects that Hubble could not detect at all. JWST's mirror is also larger, measuring over 21 feet across compared to Hubble's 7.9 feet. A larger mirror collects more light, enabling fainter objects to be detected. Combined with its infrared sensitivity, this gives JWST an enormous advantage in studying the early universe. Galaxies that were mere hints in Hubble images appear clear and detailed in JWST's view. The telescope launched on December 25, 2021, and reached its observing position about 1 million miles from Earth in early 2022. After months of calibration and testing, it released its first science images in July 2022. Those images stunned astronomers. Deep fields showed galaxies in unprecedented detail. Objects that Hubble struggled to detect blazed clearly in JWST's infrared cameras. Among those early images were the first hints of the little red dots. Researchers scanning the data noticed an unusual number of red compact objects at high redshifts. Initial estimates suggested some might be among the most distant galaxies ever seen. Follow-up observations confirmed it. JWST had opened a window into the previously hidden early universe. The telescope's spectroscopic capabilities are equally impressive. Its near-infrared spectrograph, or NIRSPEC, can analyze the light from dozens of galaxies simultaneously, breaking it down into component wavelengths. This allows astronomers to measure precise redshifts, identify chemical elements, and study the physical conditions in distant galaxies. For JADES, NIRSPEC provided the definitive redshift measurement, confirming its record-breaking distance. JWST also carries a mid-infrared instrument, MIRI, which observes at longer wavelengths. MIRI detected JADES at 7.7 microns, a remarkable feat given the galaxy's extreme distance. This detection revealed strong emission from ionized gas, indicating active star formation and the presence of oxygen. The combination of near-spec and MIRI data provided a comprehensive picture of the galaxy's properties. The advantage JWST offers is not just technical, it is transformative. Before JWST, studying galaxies at redshift 10 or higher required painstaking effort and often yielded ambiguous results. With JWST, such galaxies are readily detected and characterized. Surveys that would have taken years with Hubble can be completed in months. The pace of discovery has accelerated dramatically. This rapid accumulation of data exposed the early galaxy problem. If JWST had been slightly less capable, we might have found only a handful of distant galaxies, easy to dismiss as outliers. Instead, we found hundreds, forcing a reckoning with established models. The telescope's sensitivity and wavelength coverage made the problem impossible to ignore. JWST's advantage also lies in what it cannot do. It cannot observe invisible light as well as Hubble. For many nearby objects, Hubble's images remain superior. This is intentional. JWST was built to complement Hubble, not replace it. Each telescope excels in different areas, together covering a broader range of observations than either could alone. The discoveries JWST enabled raise a natural question. What did Hubble see, and why did it miss these galaxies? Hubble looked at the same sky and saw something completely different. The Hubble Space Telescope spent decades surveying deep fields, capturing images of the most distant galaxies it could detect. Its ultra-deep field, released in 2004, combined hundreds of hours of exposure time to reveal thousands of faint galaxies, stretching back to when the universe was less than 1 billion years old. Those images shaped our understanding of early galaxy evolution for nearly 2 decades. According to Hubble's observations, early galaxies were small, faint, and gradually increasing in number as the universe aged. At redshift 7 or 8, Hubble found a modest population of galaxies, consistent with models predicting slow, hierarchical growth. Extrapolating to even higher redshifts suggested that very few galaxies should exist at redshift 10 or beyond. The universe was still too young for significant structure to have formed. Then JWST looked at the same regions and found a completely different picture. Where Hubble saw emptiness or faint smudges, JWST revealed bright, massive galaxies. The discrepancy was stark. Hubble's infrared capabilities, though limited, should have detected the brightest of these galaxies if they were truly as luminous as JWST measurements indicated. Yet Hubble missed them. Why? The answer lies in wavelength sensitivity. Hubble's infrared camera, the Wide Field Camera 3, operates in the near-infrared but does not extend as far into longer wavelengths as JWST's instruments. For galaxies at redshift 14, most of their light has been stretched beyond Hubble's detection range. JWST picks up these wavelengths easily, revealing galaxies invisible to Hubble. But this does not fully explain the contradiction. Some of the little red dots should have been bright enough for Hubble to detect, even in its limited infrared bands. The fact that Hubble missed them suggests they might be intrinsically different from what models predicted. Perhaps their light is concentrated in wavelengths that Hubble could not observe. Perhaps dust absorbs more of their visible light than expected, or perhaps they are genuinely more abundant than pre-JWST models allowed. This discrepancy led some researchers to re-examine Hubble's data. They searched for faint red objects that might have been overlooked in initial analyses. In some cases, they found hints of galaxies that were dismissed as noise or background artifacts. Reprocessing the data with knowledge of what JWST discovered revealed that Hubble had, in fact, glimpsed a few of these galaxies. But without JWST's confirmation, those detections were too uncertain to draw conclusions from. The Hubble contradiction highlights a fundamental challenge in astronomy. Different instruments with different sensitivities can paint very different pictures of the same universe. Hubble was not wrong. It simply lacked the tools to see what JWST now reveals. Models based on Hubble's observations were reasonable, given the data available. The problem is that the data were incomplete. This incompleteness misled cosmologists. They built theories on the assumption that Hubble was seeing most of what existed at high redshift. When JWST proved that assumption false, the theories no longer fit. The universe turned out to be more complex, more populated, and more active in its early stages than Hubble's limited view suggested. Some scientists argued that the JWST discoveries do not contradict Hubble so much as extend it. Hubble provided a foundation. JWST built on that foundation, adding new flaws and revealing rooms that were always there but hidden. The two telescopes together offer a more complete view than either alone. Nonetheless, the shock of discovery remains. Astronomers expected JWST to refine our picture of the early universe, not overturn it. The sheer abundance and brightness of high redshift galaxies caught nearly everyone off guard. Even optimistic predictions fell short of what JWST observed. The Hubble contradiction forces a re-evaluation of observational cosmology. Instruments define what we can see, and what we can see shapes our theories. As instruments improve, theories must adapt. JWST represents a leap in capability, and the theories are still catching up. But the timeline itself remains a central issue. 2%. That is how old the universe was when JAD-ESG SZ140 existed. If the universe's entire history were compressed into 1 year, this galaxy appeared on January 7th. Everything before that point was darkness. The formation of the first atoms, the slow gathering of gas into primordial clouds. Everything after, the rise of countless galaxies, the formation of stars and planets, the emergence of life, happened in the remaining 358 days. The galaxy existed at the very beginning of cosmic structure, when the rulebook for how galaxies form was supposedly still being written. This 2% figure is not approximate. It comes from precise measurements of cosmic age based on the lambda CDM model. The universe is currently 13.8 billion years old, at a redshift of 14.32, corresponding to 290 million years after the Big Bang. The universe was 2.1% of its current age. The math is solid. The model is well tested. The conclusion is unavoidable. But this timeline creates impossible demands. In those 290 million years, the universe had to accomplish an extraordinary sequence of events. First, the cosmic microwave background had to decouple from matter, making the universe transparent to light. That happened at 380,000 years. Then, dark matter halos had to begin forming, pulling gas into gravitational wells. This process started perhaps 10 to 50 million years later. Next, the gas needed to cool and collapse within those halos, reaching densities high enough for nuclear fusion to ignite. The first stars probably formed around 50 to 100 million years after the Big Bang. These stars lived fast and died young, exploding as supernovae and enriching the surrounding gas with heavy elements. Subsequent generations of stars formed from this enriched gas, creating more elements and further processing the available material. Somewhere in this timeline, individual stars and star clusters had to organize into coherent galactic structures. They had to settle into rotating disks or elliptical configurations, stabilized by dark matter's gravity. This organization requires time for dynamical processes to smooth out irregularities and establish equilibrium. In modern galaxies, such processes take hundreds of millions of years. Yet JADES managed all of this by the time the universe was 290 million years old. It assembled hundreds of millions of stellar masses, created a structure over 1,600 light-years across, formed multiple generations of stars that produced detectable oxygen, and achieved a level of brightness that rivals mature galaxies billions of years older. The timeline does not seem sufficient. Some researchers proposed that the universe experienced a brief period of accelerated structure formation immediately after the Big Bang. During this period, galaxies grew faster than they ever would again. This acceleration would need to be driven by some mechanism that does not persist into later epochs. Perhaps the density of the universe was high enough that gravity pulled matter together more efficiently. Perhaps feedback from the first stars was weaker, allowing more gas to remain available for star formation. But why would this acceleration stop? What mechanism would turn off efficient galaxy formation and transition to the slower, more regulated processes we observe in later galaxies? The proposal lacks a clear physical explanation. It seems designed to fit the observations, rather than arising naturally from fundamental physics. Another idea suggested that our measurement of cosmic age might be slightly off. If the universe is actually older than 13.8 billion years, or if its expansion rate in the early epochs was slower than assumed, then galaxies at redshift 14 would have had more time to form. But changing the age or expansion history of the universe affects many other observations. The cosmic microwave background, the distribution of galaxies, and the abundance of elements formed in the Big Bang all constrain the universe's age and expansion rate. These constraints are tight. Adjusting them to give galaxies more time risks breaking agreement with other well-established data. The cosmic timeline breakdown is perhaps the most fundamental challenge posed by JADAs. It is not just one number being off or one prediction failing. It is the entire sequence of events, from the Big Bang to the formation of complex galaxies, compressed into a time frame that seems too short. Solving this requires either finding hidden efficiencies that allow processes to happen faster, or revising our understanding of when those processes began. The mystery deepened when astronomers looked closely at the stars themselves. Stars do not appear from nothing, and heavy elements cannot form in a single generation. The presence of oxygen in jades proves that multiple generations of stars had already lived and died by the time the galaxy was observed. The first generation, forming from pure hydrogen and helium, could not have produced oxygen. Those elements require stars with existing metals to catalyze their formation, or they require the explosive deaths of very massive stars to forge them. Either scenario demands a sequence of stellar births, lives, and deaths. Think of it like building a brick house. First, you need to make the bricks. That requires mining clay, shaping it, and firing it in a kiln. Only then can you construct the house. If someone finds a completed brick house just minutes after the kiln is built, you know something is wrong with the timeline. Either the bricks were made faster than physically possible, or the house was built elsewhere and transported. Neither explanation fits comfortably with physics. In jades, the bricks are heavy elements like oxygen. Making them requires stars to form, burn through their fuel via nuclear fusion, and explode. Massive stars, those more than 10 times heavier than typical ones, can accomplish this in a few million years. Smaller stars take much longer. To accumulate the amount of oxygen detected in the galaxy, you need many massive stars going through this cycle, probably across several generations. The first generation of stars forms from primordial gas. These stars are likely very massive due to the lack of metals, which normally help gas cool and fragment into smaller pieces. Massive stars burn hot and fast, fusing hydrogen into helium, then helium into carbon and oxygen, and so on up to iron. When they explode as supernovae, they scatter these elements into the surrounding gas. The second generation forms from this enriched gas. These stars incorporate the oxygen and other elements from the first generation. As they too live and die, they add even more heavy elements. With each cycle, the gas becomes richer in metals. By the time enough oxygen has built up to be detectable, several cycles have likely occurred. Each cycle requires millions of years. Fitting multiple generations into the available timeline is tight. If the first stars formed 50 million years after the Big Bang, and each generation takes about 5 to 10 million years, you can squeeze in perhaps 20 to 40 generations before reaching 290 million years. That might be enough, but it assumes everything happens at maximum speed with no delays. gas must collapse immediately into new stars after each supernova. No time is wasted. In reality, star formation is not continuous. After a supernova, the surrounding gas is heated and dispersed. It needs time to cool and recondense before forming new stars. This cooling period can take tens of millions of years, depending on conditions. If each generation requires a significant cooling time, the number of cycles that fit into the timeline drops sharply. Suddenly, producing enough oxygen becomes difficult. Some scientists suggested that the first stars were exceptionally massive, hundreds of times heavier than our closest stellar neighbor. Such monsters would burn through their fuel in just 1 million years or less, allowing many more generations to fit into the same time frame. But extremely massive stars are rare in modern galaxies. Why would they dominate the early universe? And if they did, their supernovae would be extraordinarily energetic, potentially disrupting star formation rather than enabling it. Another possibility involves overlapping generations. Instead of waiting for one generation to die before the next forms, perhaps multiple generations coexisted, forming stars simultaneously from gas in different parts of the galaxy. This parallelization would accelerate chemical enrichment without requiring individual stars to live and die faster. But it still demands rapid star formation rates and assumes the galaxy had access to vast amounts of gas from the start. The multiple generation mystery ties back to efficiency. If star formation is highly efficient, converting most available gas into stars quickly, then many stars form in a short time. More stars mean more supernovae, more heavy elements, and faster chemical enrichment. The challenge is explaining why early galaxies would be so much more efficient than later ones. No single explanation resolves the mystery fully. The timeline is tight, the physics is complex, and the observations are clear. Multiple generations of stars existed in Jades. How they managed to form, live, and die so quickly remains one of the most perplexing aspects of the early galaxy problem. Worse still, computer simulations could not reproduce these results. Astronomers rely on computer simulations to model the universe. These simulations start with the conditions immediately after the Big Bang, a hot, dense soup of particles expanding and cooling. Algorithms calculate how dark matter clumps together under gravity, how gas flows into those clumps, and how stars form from the gas. The simulations run forward in time, predicting what the universe should look like at different epochs. Comparing these predictions to observations tests whether we understand the underlying physics. For decades, simulations successfully reproduced many observed features of the universe. They matched the distribution of galaxies in the local cosmos, the structure of the cosmic web, and the properties of galaxy clusters. This success validated the lambda CDM model and the assumptions built into the simulations. Astronomers trusted that the same techniques would accurately predict the early universe. Then JWST data arrived, and the simulations failed. When researchers ran simulations forward to redshift 14, they predicted a sparse population of small, faint galaxies. At most, a few tens of objects in the surveyed volume, each containing a few tens of millions of stellar masses. These predictions aligned with Hubble observations, which had shown few galaxies at such high redshifts. The models and data agreed. Confidence was high. JWST shattered that agreement. Instead of a sparse population, it found hundreds of galaxies. Instead of small masses, it found objects rivaling the Milky Way. Instead of faintness, it found brightness exceeding predictions by factors of 10 or more. The simulations had not just underestimated the abundance and properties of early galaxies, they had missed the mark entirely. What went wrong? The simulations incorporate the best available physics for dark matter, gas dynamics, star formation, and feedback from stars and black holes. They use powerful supercomputers to solve equations governing how matter behaves under gravity, pressure, and radiation. Yet they failed to predict what JWST observed. This suggests either missing physics or incorrect assumptions. One possible missing ingredient is the efficiency of star formation. Most simulations assume that early galaxies form stars with similar efficiency to modern ones, converting around 10 to 20% of their gas into stars. If early galaxies actually converted 50% or more, the simulations would underestimate their masses and brightness. Adjusting this parameter in the models could bring them into better agreement with observations. But changing star formation efficiency requires justification. Why would it be different early on? What physical mechanism drives the change? Without answers to these questions, adjusting the parameter feels like tuning a knob to fit the data rather than deriving the behavior from first principles. It works empirically, but lacks explanatory power. Another potential issue involves feedback. Supernova explosions and stellar winds regulate star formation by heating and expelling gas. Simulations model these feedback processes, but the details are uncertain. The exact amount of energy injected, how efficiently it couples to the gas, and how long it affects star formation are all subject to assumptions. If feedback in the early universe was weaker than assumed, galaxies could retain more gas and form stars more rapidly. However, feedback physics should not change dramatically with cosmic age. Supernovae release the same energy regardless of when they occur. The way that energy affects surrounding gas depends on density, temperature, and composition, but these properties are included in the simulations. Altering feedback to fix the early galaxy problem risks making it inconsistent with observations of later epochs. A third possibility involves the initial conditions. Simulations start with density fluctuations derived from measurements of the cosmic microwave background. These fluctuations seed the formation of cosmic structure. If the fluctuations at small scales were slightly larger than current models assume, it would create more massive dark matter halos earlier, providing the scaffolding for more massive galaxies. But increasing small-scale fluctuations must be consistent with other observations, which tightly constrain the shape and amplitude of the primordial power spectrum. Despite extensive efforts, researchers have not found a simple fix that makes the simulations match JWST observations without breaking something else. Every adjustment that improves agreement at high redshift worsens it at low redshift or conflicts with other data. The simulation failure is real and persistent. This failure has profound implications. Simulations are our primary tool for understanding processes we cannot directly observe. If they fail to reproduce the early universe, our confidence in extrapolating them to other contexts diminishes. It calls into question not just specific predictions, but the entire framework we use to model cosmic evolution. Solving the simulation failure requires either discovering new physics or radically rethinking existing assumptions. Either path represents a major shift in cosmology. And then there are the deeper questions about gravity itself. What if our understanding of gravity is incomplete? Gravity seems straightforward. Mass attracts mass. The more massive an object, the stronger its gravitational pull. Einstein's general relativity describes how mass warps spacetime, creating what we perceive as gravitational attraction. The theory has passed every test thrown at it for over a century. From the orbit of Mercury to the detection of gravitational waves, general relativity works. We trust it. But what if it breaks down under certain conditions? What if the extreme environment of the early universe exposed limits to our gravitational models? Some researchers proposed that gravity might behave differently at very large scales or very early times. These modifications to general relativity, called modified gravity theories, attempt to explain observations that seem inconsistent with standard physics. One famous example is modified Newtonian dynamics, or MOND, which adjusts how gravity works at low accelerations. MOND was originally proposed to explain galaxy rotation curves without invoking dark matter. Could a similar modification explain the abundance of early massive galaxies? If gravity was slightly stronger in the early universe, matter would clump together faster. Dark matter halos would form earlier and grow more massive. This would provide the gravitational wells needed to build large galaxies in shorter timescales. The timeline crisis might evaporate if gravity gave structure formation a boost during the first few 100 million years. The challenge is making such modifications consistent with everything else we know. General relativity does not just describe how galaxies form, it governs the expansion of the universe, the bending of light around massive objects, the inspiral of merging black holes, and countless other phenomena. Any change to gravity must preserve agreement with all these observations. That is an extraordinarily tight constraint. Modified gravity theories also need to explain why the modification would turn off or become negligible after the early universe. If gravity was stronger early on, what mechanism weakened it to the strength we measure today? Physics does not usually have arbitrary cutoffs where fundamental forces suddenly change behavior. The laws of nature should be consistent across time and space. Despite these challenges, some theorists explored whether tweaks to gravity could solve the early galaxy problem. They constructed models where the gravitational constant varies with cosmic density or where additional terms in the equations of general relativity become important at high redshifts. These models can produce more massive halos earlier, potentially explaining Jades and its companions. However, when tested against other observations, most modified gravity theories encounter problems. The cosmic microwave background is exquisitely sensitive to how gravity behaves in the early universe. Any modification strong enough to significantly boost structure formation would leave detectable imprints on the microwave background radiation. Those imprints are not observed. The microwave background matches predictions from standard general relativity, combined with dark matter and dark energy. Similarly, gravitational lensing, the bending of light by massive objects, provides independent tests of gravity. Observations of lensing by galaxy clusters agree with general relativity's predictions. No evidence suggests gravity behaves differently than expected. These observations severely limit how much you can modify gravity without creating new conflicts. A more subtle possibility involves quantum gravity effects. At extremely high densities and energies, such as those present in the very early universe, quantum mechanics and gravity interact in ways we do not fully understand. Our current theory of gravity is classical, not quantum. A complete theory of quantum gravity might reveal new phenomena that affect how structure forms. But quantum gravity operates at scales much smaller than galaxies. Its effects are usually confined to black hole singularities and the first fractions of a second after the Big Bang. Extending those effects to influence galaxy formation hundreds of millions of years later requires mechanisms that do not currently exist in theory. It is speculative at best. The gravity question remains open but unlikely to provide the answer. Most physicists believe general relativity is correct within the regime where galaxy formation occurs. The early universe was dense and hot, but not so extreme that classical gravity breaks down. If the solution lies elsewhere, modifying gravity seems like the wrong direction. Yet the question persists because the alternatives are equally troubling. Lambda CDM is the standard model of cosmology, and it has been remarkably successful. Lambda represents dark energy, the mysterious force driving the accelerated expansion of the universe. CDM stands for cold dark matter, the invisible substance that provides the gravitational scaffolding for galaxies. Together with ordinary matter and the known laws of physics, Lambda CDM explains a vast range of observations. The cosmic microwave background, the large-scale distribution of galaxies, the abundance of elements, and the expansion history of the universe all fit within this framework. For decades, Lambda CDM stood as one of the most thoroughly tested scientific models. Every new observation seemed to confirm its predictions. When small discrepancies arose, tweaking a parameter or refining a measurement usually resolved them. The model felt robust, almost unshakable. Then JWST started finding galaxies that should not exist. The challenge Jades poses to Lambda CDM is not that it violates a specific prediction, It is that the galaxy's existence requires conditions the model does not naturally produce. Lambda CDM predicts how many dark matter halos of each mass should exist at different times. It predicts how efficiently gas should cool and form stars. It predicts the timeline for structure formation. JADES defies these predictions simultaneously. Some researchers argued that the observations do not actually break Lambda CDM. They propose that the model is correct, but our interpretation of the data is wrong. Perhaps the galaxies appear more massive than they truly are because of bright black holes artificially inflating their luminosity. Perhaps dust is distorting colors and leading to incorrect distance estimates. Perhaps we are misidentifying some objects as galaxies when they are actually something else. These alternative explanations had merit, and follow-up observations tested them. Spectroscopy confirmed distances, ruling out most misidentification issues. Analysis of light distribution showed that many galaxies are too extended to be dominated by central black holes. Dust could explain some reddening, but not the extreme brightness and mass. One by one, the alternative explanations fell short. That left two options. Either Lambda CDM needs modification, or some unknown physics is at play within the Lambda CDM framework. Modifying the model could involve changing the properties of dark matter, adjusting the early expansion rate, or introducing new components like early dark energy. Each modification has consequences that must be checked against other observations. For example, some theorists proposed adding extra dark energy in the early universe. This would accelerate expansion initially, then fade away, leaving the late-time behavior unchanged. Early dark energy could alter the timing of structure formation, potentially allowing galaxies to form faster. Models incorporating this idea showed some promise in producing more massive galaxies earlier. But early dark energy also affects the cosmic microwave background in specific ways. Detailed analysis of microwave background data found no strong evidence for the amount of early dark energy needed to solve the galaxy problem. The constraints are tight. You can add a little without conflict, but not enough to fully explain JADES-0. Another approach questioned the nature of dark matter. Standard Lambda CDM assumes dark matter is cold, meaning it moves slowly and clumps efficiently on all scales. But what if dark matter has additional interactions beyond gravity? What if it can collide with itself or decay into lighter particles? These modifications would change how halos form and evolve, possibly creating different conditions for galaxy formation. Self-interacting dark matter has been explored extensively. In some regimes, it can make halos denser or alter their internal structure. Whether this helps or hinders early galaxy formation depends on the details. Most studies found that self-interactions do not dramatically change the abundance of massive halos at high redshift. The effects are too subtle to resolve the tension. A more radical possibility involves questioning the Lambda CDM framework entirely. Perhaps the Big Bang model is incomplete. Perhaps inflation, the rapid expansion thought to occur in the first fractions of a second, proceeded differently than assumed. Perhaps the initial conditions of the universe were not as smooth as the cosmic microwave background suggests on small scales. These ideas venture into speculative territory. Lambda CDM is built on decades of observations and theoretical development. Discarding it requires overwhelming evidence that something is fundamentally wrong, not just a handful of unexpected galaxies. As one researcher put it, you do not throw out a theory that has survived 1,000 tests because of one new puzzle. You first exhaust all possibilities within the existing framework. The Lambda CDM challenge is not existential yet. The model is strained but not broken. However, if more observations confirm the abundance and properties of early massive galaxies, the strain will grow. At some point, a new framework might be needed, one that incorporates whatever physics Lambda CDM is missing. But before abandoning the standard model, astronomers looked at another cosmic puzzle. After the first stars ignited, they began changing the universe around them. Early stars emitted intense ultraviolet radiation. This radiation had enough energy to strip electrons from hydrogen atoms, a process called ionization. Initially, the universe was filled with neutral hydrogen. Light could not travel far through it without being absorbed, but as more stars formed and pumped out ultraviolet photons, bubbles of ionized gas expanded around them. These bubbles grew, eventually overlapping and merging. The universe transitioned from mostly neutral to mostly ionized, a period called reionization. Reionization is one of the major phase transitions in cosmic history. It fundamentally altered the properties of intergalactic gas, affecting how galaxies could form and evolve. Understanding when and how reionization occurred provides crucial insights into the early universe. Observations of the cosmic microwave background indicate that reionization was mostly complete by about 400 million years after the Big Bang. The timeline matters. For reionization to finish by 400 million years, enough stars must have formed earlier to generate the required ultraviolet radiation. This means a substantial population of galaxies must have existed by 300 to 400 million years after the Big Bang, actively producing young, hot stars. The more galaxies, the faster reionization proceeds. JDs and the other little red dots fit this picture perfectly, except for one problem: they are too massive. Reionization models assumed the ionizing photons came from numerous small, faint galaxies, not from a smaller number of massive, bright ones. The discovery that massive galaxies were common early on forces a reconsideration of which sources drove reionization. If galaxies like JDs dominated the early universe, they could have reionized their surroundings very efficiently. Massive galaxies form stars at higher rates, producing more ultraviolet photons. They also retain more gas due to their stronger gravity, allowing sustained star formation. This combination makes them powerful ionizing sources. A few dozen massive galaxies in a given region might ionize as much volume as hundreds of smaller ones. However, massive galaxies also experience more feedback from supernovae and stellar winds. This feedback can heat the surrounding gas, making it harder for ionizing photons to escape into the intergalactic medium. If the photons are trapped inside the galaxy, they contribute less to reionization. The balance between star formation rate and photon escape fraction determines how effective a galaxy is at reionizing the universe. Observations of JDAs showed strong emission lines from ionized oxygen and hydrogen. These lines indicate that ionizing photons are present within the galaxy, but whether they escape into surrounding space remains unclear. Measuring escape fractions for high redshift galaxies is challenging. It requires detecting faint ultraviolet light that has been heavily redshifted and comparing it to the galaxy's total ionizing output. Some studies suggested that early massive galaxies had lower escape fractions than smaller ones. Their deeper gravitational wells trapped more photons, reducing their contribution to cosmic reionization. If true, then despite their brightness, these galaxies were not the primary drivers of reionization. Smaller, fainter galaxies still did most of the work. Other research found evidence for higher escape fractions in certain early galaxies. Compact, star-forming regions could create channels through which ionizing radiation leaked out. If enough of these channels existed, even massive galaxies could contribute significantly to reionization. The question remained open, dependent on observations that are difficult to obtain. The reionization puzzle also connects to the abundance of early galaxies. If massive galaxies are common, they change the ionizing photon budget. More photons mean reionization could have started earlier or proceeded faster than previously thought. This affects when the first stars formed and how quickly structure developed. It ties directly back to the timeline crisis. Recent analysis of the cosmic microwave background provided clues about reionization timing. The polarization pattern in the microwave background is sensitive to when free electrons reappeared in the universe. Measurements suggest reionization began around 450 million years after the Big Bang, and completed by 400 million years. This narrow window constrains the star formation history. For reionization to occur in that window, a substantial population of star-forming galaxies must have existed by at least 500 million years after the Big Bang, with many forming even earlier. Jades, existing at 290 million years, fits within this timeline, but its mass and brightness suggest it represents a mature phase of galaxy evolution, not the very beginning. If galaxies this developed existed by 300 million years, when did the first proto-galaxies form? 50 million years? 100 million years? The timeline becomes increasingly compressed. The reionization puzzle does not directly contradict Jades' existence, but it adds another layer of complexity. Explaining the galaxy requires explaining not just how it formed, but how it fits into the broader context of cosmic reionization. The two phenomena are linked, and solving one helps constrain the other. Yet another explanation emerged, involving ancient monsters. What if some black holes formed directly from the Big Bang itself? Standard black holes form when massive stars collapse at the end of their lives. The star exhausts its nuclear fuel, loses the pressure support that held it up against gravity, and implodes. If the core is heavy enough, it collapses into a singularity surrounded by an event horizon. This process creates stellar mass black holes, typically 10 to 100 times heavier than individual stars. Supermassive black holes, those millions or billions of times more massive, cannot form this way. There is no single star big enough. Instead, they grow through accretion and mergers over long periods. But as we have seen, growing a supermassive black hole from a stellar mass seed in less than a few 100 million years is difficult. The Eddington limit restricts how fast black holes can consume matter. Primordial black holes offer a different pathway. These would have formed in the extremely hot, dense conditions right after the Big Bang. If certain regions of the early universe were slightly denser than average, they could have collapsed directly into black holes without going through the stellar phase. The mass of these primordial black holes depends on the size of the overdense region, ranging from microscopic to potentially millions of stellar masses. If primordial black holes existed, they could seed the supermassive black holes we observe in galaxies today. Starting with a black hole already weighing thousands or millions of times, a typical star's mass bypasses the slow growth phase. Even modest accretion rates would quickly build such objects into the supermassive black holes, powering quasars and bright galactic nuclei. This theory could explain some of the little red dots. If many of them host primordial black holes that are actively accreting, their brightness could come from the black hole rather than stars. This would make the galaxies appear more massive than they truly are. Remove the black hole contribution, and the galaxies shrink to sizes compatible with standard models. Observations provide some support for this idea. Several little red dots show spectroscopic features consistent with active black holes. Broad emission lines, high-energy radiation, and compact light distribution all point to central engines. If primordial black holes explain these objects, the tension with lambda CDM eases. However, not all little red dots fit this pattern. Many show light distributed across extended regions, indicating stellar populations rather than point sources. Their spectra match expectations for young, star-forming galaxies without dominant black hole contributions. JADES GSZ140 falls into this category. While it shows signs of ionized gas emission, likely from star formation, its size and light distribution argue against a central quasar dominating its luminosity. For primordial black holes to fully solve the early galaxy problem, they would need to be common. Finding one or two might be a curiosity, but finding hundreds suggests they represent a significant population. This raises questions about their formation. What conditions in the very early universe would produce large numbers of primordial black holes? Typical inflationary models do not predict them. You need special conditions, such as large density fluctuations on small scales or phase transitions that create concentrated regions of energy. Theoretical work explored these possibilities. Some models found that certain inflationary scenarios could generate enough density fluctuations to produce a population of primordial black holes. But these models also predict other effects, such as increased gravitational waves from the early universe or distortions in the cosmic microwave background. Searches for these signals have so far come up empty. Another concern involves the fate of primordial black holes. If they formed in large numbers, many would still exist today, scattered throughout the universe. Some might make up part of the dark matter. Searches for such objects, using gravitational lensing and other techniques, have constrained how much dark matter can be in the form of primordial black holes. The limits are fairly tight. They cannot make up more than a small fraction of total dark matter without conflicting with observations. The primordial black hole theory remains speculative. It offers a potential explanation for some observations but does not fully resolve the early galaxy problem. It also introduces new questions about the early universe that lack clear answers. Like modified gravity, it addresses the symptoms without providing a complete cure. What troubles some scientists most is what these discoveries mean for us. Understanding our cosmic past is not just academic curiosity. The history of the universe connects directly to our existence. Stars form, live, and die, creating the heavy elements needed for planets and life. Galaxies provide the environments where stars can form over billions of years. The timeline of cosmic evolution determines when and where life could arise. If that timeline is wrong, our understanding of how we came to exist is incomplete. Jade suggests the universe became structured and chemically enriched far earlier than we thought. If massive, metal-rich galaxies existed when the cosmos was only 2% of its current age, then the conditions for planet formation and potentially life arose much sooner. This shifts the timeline for when the first habitable environments could have appeared. Some researchers pointed out that early, massive galaxies are not necessarily friendly to life. They form stars at prodigious rates, flooding their surroundings with radiation. Supernovae explode frequently, sterilizing nearby regions. The intense star formation and energetic processes might make such galaxies hostile environments despite their chemical richness. But the point remains, if galaxies evolved faster than expected, the universe became capable of supporting complex structures sooner. This has implications for the Drake equation, which estimates the number of intelligent civilizations in the galaxy. One factor in that equation is the rate of star formation and the age of suitable stars. If star formation ramped up earlier and more vigorously, there could have been more opportunities for life to develop across cosmic history. The anthropic principle, the idea that the universe's properties must be compatible with our existence, also comes into play. Some formulations of the anthropic principle suggest that we observe the universe at a particular time and place because those conditions allow observers to exist. If the universe's early history was wildly different than we thought, does that affect anthropic reasoning? Consider this. If galaxies like Jades are common, then rapid structure formation is the norm, not the exception. The universe we inhabit, with its particular rate of galaxy growth and star formation, might be typical. But our models, which predicted slower growth, were based on incomplete data. We built theories around what Hubble could see, missing the fuller picture JWST revealed. Our anthropic reasoning was constrained by observational bias. There is also a philosophical angle. Humans have repeatedly discovered that we are not central or special in cosmic terms. Earth is not the center of the solar system. The solar system is not the center of the galaxy. The galaxy is one of billions. Each discovery displaced humanity from a position of cosmic importance. The early massive galaxies add another layer. Even our timeline, the narrative of how the universe slowly built up structure over billions of years, may be less gradual than we thought. The cosmos was already busy forming complex structures while we imagined it to be in its infancy. This humility is valuable. It reminds us that the universe does not care about our preconceptions. Nature operates according to its own rules, and our job is to uncover those rules through observation and reason. When observations conflict with theory, we adjust the theory, not the observations. But there is a more immediate implication. If our understanding of the early universe is fundamentally flawed, what else might we be wrong about? Dark matter, dark energy, the nature of gravity, the fate of the cosmos all rest on the same foundational cosmology. If that foundation has cracks, the entire edifice might need reinforcement or rebuilding. This is not to suggest panic or despair. Science advances by finding and correcting errors. The discovery of early massive galaxies is an opportunity to refine our models, not a failure of science. But it does underscore how much we still do not know. The universe is vast, ancient, and complex. Our observations capture only a fraction of its behavior. Humility and openness to revision are essential. For now, the anthropic implications remain speculative. We do not yet know how to fully reconcile Jades with our cosmic timeline. Until we do, the broader philosophical questions remain unanswered. Meanwhile, certain galaxies stood out as especially problematic. 6 galaxies became infamous as the universe breakers. These objects, identified in the Cosmic Evolution Early Release Science Survey, appeared so massive and so distant that they seemed to violate basic cosmological principles. Initial estimates placed them at redshifts between 9 and 12, with stellar masses comparable to or exceeding the Milky Way. If confirmed, they would represent an existential crisis for Lambda CDM. The universe simply did not have enough time or dark matter halos to build such objects. The term universe breakers was not official nomenclature. It was a catchy label used in headlines and discussions to capture the shocking nature of the discovery. But it stuck, reflecting genuine concern among cosmologists. These 6 galaxies, more than any others, encapsulated the early galaxy problem. Each one showed up as a red dot in JWST images. Photometric analysis suggested extreme distances and high masses. The combination seemed impossible. Critics immediately questioned whether the measurements were accurate. Perhaps these were not distant galaxies at all, but closer objects masquerading as early ones. Perhaps their colors were distorted by dust or unusual stellar populations. Spectroscopy would settle the debate, and astronomers prioritized follow-up observations. One by one, the universe breakers came under scrutiny. The first spectroscopic result delivered a surprise. One of the 6 turned out to be much closer than initially thought, at a redshift of 5.6 rather than 16. It hosted an actively feeding black hole that dominated its light output, making it appear brighter and redder than a typical galaxy at that distance. This object was not a universe breaker after all. That discovery tempered some of the alarm. If one of the 6 was misidentified, others might be as well. But it also highlighted a real phenomenon. Some high redshift galaxies do host bright black holes that complicate mass estimates. Disentangling black hole light from starlight requires careful analysis. The remaining 5 universe breakers awaited spectroscopic confirmation. Early indications suggested that at least some of them were genuinely at high redshift, though perhaps not as high as the most extreme initial estimates. Even if their redshifts dropped from 16 to 10 or 11, they would still pose significant challenges. Massive galaxies at redshift 10 are nearly as problematic as those at redshift 16. The universe breakers forced astronomers to confront measurement uncertainties. Photometric redshifts, while useful for quick surveys, are not infallible. They depend on assumptions about galaxy spectra, which can be violated in unusual objects. Early galaxies might have stellar populations or dust properties different from those used to calibrate photometric techniques. This could lead to systematic errors in distance estimates. Researchers developed more sophisticated photometric methods. incorporating broader ranges of possible spectra and accounting for black hole contributions. Reanalysis of the universe breakers using these improved techniques adjusted some redshifts downward. The objects remained distant, but not quite as record-breaking as first thought. Still, the fact that even a few massive galaxies existed at redshifts above 10 was noteworthy. Lambda CDM predicted such objects should be extraordinarily rare, perhaps one in the entire observable universe at that epoch. Finding several in a relatively small survey area suggested either incredible luck or an underestimation of their abundance. The universe breakers also exemplified the importance of confirmation. In the fast-paced world of modern astronomy, preliminary results often leak before full analysis is complete. The initial announcements about these galaxies generated significant media attention and scientific debate. When subsequent data showed that at least one was not as extreme as claimed, some viewed it as a retraction or failure. In reality, it was science working as intended. Preliminary findings get tested, refined, and sometimes revised based on better data. The true universe breakers, if they exist, are still being sought. JWST continues to survey deep fields, accumulating data on thousands of high redshift galaxies. Among them might be objects so massive and so distant that no amount of theoretical adjustment can explain them within lambda CDM, or perhaps the most extreme cases will all be explained away, leaving a residual population of merely very massive early galaxies rather than impossibly massive ones. Either outcome has implications. If the universe breakers disappear under scrutiny, it suggests the early galaxy problem is real but not catastrophic. The models need tuning, not replacement. But if they persist, cosmology faces a reckoning. The only way to know for certain was through rigorous confirmation. Photometry gives you a hint. Spectroscopy gives you certainty. When JWST captures an image, it records the brightness of objects in several filters, each sensitive to different wavelengths. By comparing how bright a galaxy appears in each filter, astronomers estimate its redshift. This photometric method is fast, allowing surveys of thousands of galaxies. But it is also imprecise. Uncertainties of 10 to 20% are common. In extreme cases, misidentifications occur. Spectroscopy removes the ambiguity. Instead of measuring brightness in broad filters, a spectrograph splits the galaxy's light into its component wavelengths, creating a spectrum. This spectrum reveals emission and absorption lines from specific elements. Each element produces lines at characteristic wavelengths. By identifying which lines are present and measuring how much they have been shifted, astronomers determine the redshift with high precision. Errors drop to less than 1%. For spectroscopy was essential. The initial photometric estimate suggested a redshift around 14, placing it among the most distant objects ever detected, but confirmation required a spectrum. In October 2023, the JADIS team used JWST's NearSpec instrument to observe the galaxy for over 10 hours, accumulating enough light to produce a detailed spectrum. The spectrum showed clear emission lines from hydrogen and oxygen. These lines, known as Lyman alpha and oxygen 3, are produced by hot, ionized gas in star-forming regions. Measuring their wavelengths gave a redshift of 14.32, confirming the photometric estimate. JADIS was genuinely one of the most distant galaxies ever observed. The spectroscopic confirmation did more than verify distance. It revealed the galaxy's physical properties. The strength of the emission lines indicated vigorous star formation. The presence of oxygen showed that multiple generations of stars had enriched the gas. The lack of broad lines ruled out a dominant quasar contribution, supporting the interpretation that starlight, not a black hole, powered the galaxy's luminosity. This level of detail is impossible to obtain from photometry alone. Spectroscopy transforms a fuzzy red dot into a characterized astrophysical object with measurable properties. It provides the data needed to test theoretical models and constrain formation scenarios. Across the population of little red dots, spectroscopic follow-up proceeded more slowly. Spectroscopy is time-intensive. Each galaxy requires hours of observation to gather sufficient light. JWST's observing time is precious, allocated through competitive proposals. Astronomers must prioritize which objects to observe. The most interesting candidates get spectra first, others wait. By late 2024, spectroscopy had confirmed dozens of high redshift galaxies. Most matched their photometric redshift estimates reasonably well. A few turned out to be closer than expected, their colors affected by dust or unusual stellar populations. But the majority held up under scrutiny. The abundance of massive galaxies at high redshift was real. One interesting pattern emerged from the spectroscopic data. Many early galaxies showed unusually strong emission lines relative to their continuum light. This indicated that a large fraction of their light came from ionized gas rather than stars. Strong emission lines can make galaxies appear brighter in certain filters, potentially biasing photometric mass estimates upward. When corrected for this effect, some galaxies appeared less massive than initially thought. This correction helped ease the tension with lambda CDM slightly but did not eliminate it. Even after adjusting for emission line contamination, the galaxies remained more massive and abundant than standard models predicted. The problem persisted. Spectroscopy also enabled studies of galaxy kinematics, the motion of gas and stars within the galaxy. By measuring the width of emission lines, astronomers inferred how fast gas was moving. Broad lines indicate rapid motion, suggesting deep gravitational wells and high masses. Narrow lines suggest less massive systems. For jades, the emission lines were moderately broad, consistent with a massive galaxy but not extreme. The spectroscopic confirmation campaign continues. Every new spectrum adds to the database of well-characterized early galaxies. Patterns emerge. Some galaxies are dominated by black holes. Others are pure starbursts. Some show signs of mergers or interactions. Each piece of data refines our understanding. Without spectroscopy, the early galaxy problem would remain ambiguous. Critics could always argue that photometric redshifts are unreliable, that the galaxies are not as distant or massive as claimed. Spectroscopy removes that escape hatch. The distances are confirmed. The masses, while subject to modeling uncertainties, are broadly consistent with photometric estimates. The observations are solid. This left theorists with no choice but to take the problem seriously. When observations clash with models, theorists get creative. Dozens of papers appeared in the months following JWST's early discoveries, each proposing explanations for the abundance and properties of high redshift galaxies. Some invoked new physics. Others tweaked existing models. A few suggested the problem was not as severe as it seemed. The competition among theories reflected both the importance of the puzzle and the difficulty of solving it. One popular approach involved boosting star formation efficiency. If early galaxies converted 70 to 80% of their gas into stars, instead of the usual 20%, they could reach observed masses more quickly. Researchers proposed mechanisms to achieve this. Lack of heavy elements might prevent gas from fragmenting into small clouds, forcing it to collapse into larger, more efficient star-forming clumps. Weaker feedback from the first generation of stars might allow more gas to remain bound to the galaxy. Dense, dark matter halos might resist gas expulsion better than modern ones. These ideas had merit, but required fine-tuning. The efficiency boost needed to be strong enough to explain observations, but not so strong that it overproduced galaxies at later times. It also needed a physical justification, not just an ad hoc parameter adjustment. Some models achieved this by tying efficiency to metallicity or halo density, creating a natural transition as the universe evolved. Another theory focused on the initial mass function, the distribution of stellar masses at birth. In modern galaxies, most stars form with low masses, with only a small fraction becoming massive stars. But if the early universe preferentially formed massive stars, each generation would produce more heavy elements and more ionizing radiation. This could accelerate chemical enrichment and galaxy assembly. Observations of distant galaxies showed hints that the initial mass function might indeed be different at high redshift. Some spectra suggested an overabundance of massive stars compared to local galaxies. But the evidence was not conclusive. Measuring the initial mass function from spectra is tricky, requiring assumptions about stellar populations and dust. A third approach questioned the role of black holes. If many little red dots hosted actively accreting black holes, their brightness would be artificially inflated. Subtracting the black hole contribution would reduce the inferred stellar masses, bringing them into line with predictions. This theory explains some objects well, particularly those with quasar-like spectra, but it struggled with galaxies like JDs, which showed extended light distributions inconsistent with central black holes. Modified cosmology offered a more radical solution. Some theorists proposed adding early dark energy to the universe's energy budget. This additional component would alter the expansion rate during the first few 100 million years, changing the timeline for structure formation. With more time or different conditions, massive galaxies could form earlier. However, as discussed earlier, early dark energy must not conflict with cosmic microwave background observations, which tightly constrain its properties. Another cosmological modification involved changing the primordial power spectrum, the pattern of density fluctuations from inflation. If fluctuations on small scales were larger than assumed, more massive dark matter halos would form early. This could seed the observed massive galaxies. But increasing small-scale power affects other observable quantities, like the number of satellite galaxies around the Milky Way. Balancing these constraints is challenging. A few researchers explored even more exotic ideas. Variable speed of light theories, where the speed of light was different in the early universe, could alter distance calculations and timeline. Extra dimensions or modifications to quantum mechanics in extreme conditions might affect how matter clumped. These theories remained highly speculative, lacking both experimental support and clear predictions. The competing theories shared a common feature. None provided a complete, satisfying explanation that addressed all aspects of the early galaxy problem without introducing new issues. Each explained part of the puzzle or worked under certain assumptions. This suggested the solution might involve multiple factors, not a single silver bullet. Perhaps early galaxies did form stars more efficiently, and they benefited from a top-heavy initial mass function, and some hosted bright black holes, and the primordial power spectrum had slightly more small-scale power than assumed. Each contribution small, but together sufficient to explain observations. Such a multifaceted solution would be harder to test but might be closer to reality. The debate continues in journal articles, conference presentations, and online discussions. As more data arrives from JWST and other telescopes, some theories gain support while others fade. The process is messy, contentious, and exactly how science should work. The future holds more answers than we currently have. JWST is just the beginning. The telescope will continue operating for years, possibly over a decade if its systems remain healthy. Each year brings new surveys, deeper observations, and more refined measurements. The database of high redshift galaxies will grow from hundreds to thousands. Patterns invisible in small samples will emerge. Rare objects will be found. The early universe will come into sharper focus. Spectroscopic campaigns are expanding. Astronomers are obtaining spectra for larger samples of little red dots, characterizing their properties in detail. These data will reveal whether the brightest objects are dominated by stars or black holes, how common chemical enrichment is, and whether certain galaxy types are more abundant than others at specific redshifts. Every spectrum adds a data point that models must explain. JWST is also pushing to even higher redshifts. If galaxies exist at redshift 15, 16, or beyond, JWST might find them. Discovering galaxies even earlier than JDS would further compress the timeline, intensifying the crisis. Alternatively, finding a cutoff, a redshift beyond which galaxies become scarce, would provide a crucial constraint on when structure formation began. Ground-based telescopes complement JWST's work. The Atacama Large Millimeter Array, ALMA, observes in millimeter and submillimeter wavelengths, detecting coal dust and molecular gas in distant galaxies. ALMA confirmed the oxygen detection in JADES and will do the same for other candidates. These observations probe the raw material for star formation, revealing how much gas early galaxies contained and how efficiently they used it. Future facilities will push capabilities even further. The extremely large telescope, currently under construction in Chile, will have a mirror over 130 feet across. Its light-gathering power will dwarf existing telescopes, enabling detailed spectroscopy of faint, distant objects. It will resolve structures within high redshift galaxies, mapping star-forming regions and measuring rotation curves. This information will constrain dark matter distributions and test formation models. NASA is planning a successor to JWST, though it remains in early concept stages. This telescope might observe at even longer wavelengths or employ new technologies to boost sensitivity. Whatever form it takes, it will aim to answer questions JWST raises, probing deeper into cosmic history and exploring the epoch when the very first stars ignited. Gravitational wave astronomy also promises insights. Future detectors, more sensitive than current instruments, might detect mergers of black holes or neutron stars from the early universe. These events carry information about stellar populations and black hole formation pathways. Observing gravitational waves from the epoch of JADES would provide an independent probe of conditions in the early universe. Theoretical work will proceed in parallel. Improved simulations, running on more powerful computers, will incorporate lessons learned from JWST observations. Researchers will test different star formation models, feedback prescriptions, and initial conditions. The goal is to find a set of parameters that reproduces observations across all epochs, from the earliest galaxies to the present day. International collaboration will accelerate progress. Astronomers from around the world share data, compare results, and challenge each other's interpretations. Open access to JWST data allows anyone to analyze it, not just the original observers. This democratization of data ensures that good ideas can come from anywhere, not just established institutions. The ultimate question is whether future observations will resolve the early galaxy problem or deepen it. If refined measurements show that the galaxies are not as massive as initially thought, or if theoretical adjustments prove sufficient to explain them within lambda CDM, the tension will ease. Cosmology will remain intact, merely refined. But if the observations hold up and the discrepancies persist, we face a more profound challenge. We may need to revise fundamental aspects of how we understand the universe's history. New physics might be required, old assumptions might be discarded. The process will be uncomfortable but necessary. Science thrives on such moments. When observations overturn expectations, knowledge advances. The discovery of cosmic acceleration, dark energy, and the accelerating expansion of the universe shocked cosmologists in the late 1990s. It contradicted assumptions about the universe's fate, yet it led to Nobel Prizes and a deeper understanding of reality. JADES and its companions might be triggering a similar revolution. We stand at the edge of new knowledge. The early universe is revealing itself in ways we never anticipated. What we thought we knew is being tested. What we will learn remains uncertain. But one thing is clear. The cosmos is stranger, more dynamic, and more surprising than our models suggested. The galaxy so far away that it raises troubling questions is not just a puzzle. It is an invitation to look deeper, think harder, and accept that the universe will always have more to teach us.